Alrighty, so we're moving on into the next section, and we're going to start talking about something called rate of change. All right, so before, what you just got done doing is we were talking about, is this proportional? And so what you did is you looked at some sort of input-output table of X and Y, and you started looking at, all right, what is my dependent variable divided by my independent variable? What's Y divided by X? And see if that is the same each and every time. If is there one particular constant that you multiply X by, and you'll always get your input to get the output. There we go. So now we're going to take a little step further, and we're going to talk about the rate of change. Okay, now a rate is going to be written as a ratio again, all right? And the numerator is going to be whatever my changes in my Y value, okay? Or the Y value is also known as the dependent variable or the output. There's a lot of different terms kind of depending on the situation. That's the numerator. In the denominator, we're going to figure out how much did you change in your X value. Your X value is the independent one, the independent variable, and it's your input, okay? You could also think of it this way. This is the vertical change because the y-axis is the vertical one, and the x-axis is the horizontal one, all right? So this is what we're going to talk about now. And so really what we're looking for is grab a couple of points, whether it's in a table or on a graph, and we're going to talk about how much did it change to get from this point to this point. And so we start thinking, well, how much did I change vertically? So against the y-axis, you're looking at how much did it change this way versus how much did it change horizontally. Okay. Now, what I say is that I get really tired of writing this change in Y value, change in X value all the time. So, as many good mathematicians do, we find a way to shorten that up. And the way that stuck for me, that was easy, is using the Greek letter delta, which basically looks like a triangle. And in math, either that symbol is going to represent a triangle, or in this case, it stands for the change in. So the change in the Y value over the change in the X value. You're going to make this ratio. We're going to analyze and look at that value. And today what we're going to look at is, all right, do these, as I look from interval to interval, from here to here, from here to here, here to here, do I get a constant rate of change, meaning from here to here to here, I'm progressing at a nice constant rate? Or is the situation that I've got kind of going up or down, maybe a little flatter part, a moderate part, maybe really steep? What is my data telling me? It tells a story all the time, and you're just trying to figure out, is it constant or does it vary? So let's take a look at one or two examples and get you a feel for what's going on. Alrighty? All right, here's some information. In fact, grab some paper for your notes right now, and let's write what this table is representing here. All right, on the top row, it's the months. Month 2, month 3. Notice they don't always go in order or by one increment at a time, and that's okay. Not everything happens that way. This is your input or your X value. This is the independent variable. The temperature. So what this graph is from is, this is showing average temperature for 5 months in a particular city. Find the rate of change for each time period, and then during which time period did the temperature increase at the fastest rate. All right, this is input, this is output. That's the Y variable here, and that's going to be temperature. Now, when we're talking about how did it change during which time period, we have to look at a starting and an ending point. So the first interval I'm going to look at is from month 2 to month 3. I'm going to take this fraction, which is now the change in the Y value, that's temperature, over change in the X value, that's months. So sometimes it's helpful. I think if you have labels, put labels in there. This is degrees and this is months. So in this interval from month 2 to month 3, I increased 1 month, but that's my denominator. My temperature, 56 to 56, that's just 0. So my first rate of change is 0 degrees in 1 month, okay? Or just 0, number value-wise. Next one, from month 3 to month 5. 3 to 5. Let's see here. This time, it was a 2-month increase in the denominator. My temperature went from 56 to 63. That's an increase of 7 degrees. So this one is 7 over 2. If we simplify that and make it a unit rate, take 7 divided by 2, because then that will give me the value in degrees for 1 month. 7 divided by 2 is 3.5, or 3.5. All right, next interval. Next interval is, I'm going to scooch this here. All right, from month 5 to month 7. Let's take a look here. 5 to 7, that's 2 months' time. And this time it increased 8 degrees. Alrighty, let's see here. Simplify this into a unit rate so you get 1 month's time. This would be 4. These two are really close. 3.5 degrees in a month, 4 degrees in 1 month. But this one is a little larger, which means it's going to be a little steeper. The last one is month 7 to month 8. 7 to 8. All right, this time again, it's 1 month. My temperature only went up 1 degree. So that's already actually built in to be a unit rate, 1 degree in that 1 month time frame. So we have 4 rates of change, and each one of them has a different value. What this tells me is that this is a relationship that has varying or variable rates of change. We're going to graph this now so you can see what this would look like. All right, I'm going to go to the next screen because then I have the table built in here. So hang on. All right, let's build a graph with this data so you can kind of see what this means. All right, X value, my horizontal axis is months. Let's label it. Now, granted, we're just sketching it here. If I was being really particular, I'd probably get graph paper, or even better yet, use some kind of technology to make sure it's exact. But for our purposes, I just want to get a general idea, and we'll do some good estimating, all right? All right, here's my months. My y-axis is temperature in degrees Fahrenheit. Now I've got to get all the way up to 72, and so I'm certainly not going to use intervals of 1. That would be insane. So I think what I'll do is do intervals of 10. So let me spread these out and get these lined up here. 10, 20, 30, 40, 50, 60, 70, 80. Go ahead and get yours done and get yours labeled. I'm listening to kind of wintry music since it's still snowing outside and it's only October. Crazy. I like snow though, so it's good. Okay, here we go. Month 2, I get a data point of 56. So here's where 50 is, and 56 is going to be just on the high side of the middle, between 50 and 60. Month 3 has the same temperature value. So as I put that on here, it'll be at the same level, and go ahead and connect those. Ooh, I'm going to have to move this graph already. I can see I'm going to get into trouble, huh? All right, I better move this down here. Over here, maybe over here. That way, things won't be in the way. All right, let me erase this. Okay, next data point to plot. Let's get that one in. At month 5, it's 63. So 5 is about there, 63 about there. Connect them. Month 7 is 71. So I don't have any data at month 6. That looks better. Month 7, 71. Probably right about there. And month 8, gosh, these look way over. I must be slanted. Month 8 is at 72, which should be just a tiny bit higher. So we go like this, and then maybe like that. Clearly that's not perfect, but we're getting an idea that definitely, because it started out flat, this particular set of data does not give me a constant rate of change. These are varying, so we're going to call it a variable rate of change. As you look at it and try to measure it, when we're thinking the change in the y value and the change in the x value as you go from one to the next, you'll see why this is 0, this was 3.5, this one was 4, and this one was 1. So basically, the beginning should look totally flat. The last section there should be not as steep as these two. These probably look almost exactly the same, which is why it's good to back up your idea with the actual math to make sure, because you might think, oh, it's a constant between here and here, but actually it's not. When we do things by hand, it doesn't always look quite right. In fact, on this one, which was generated electronically, they almost look exactly the same as well. And really, this chunk here is just a tiny bit steeper. Plays games with your eyes, okay? All right, let's look at some other ones so you're kind of getting the hang of this, all right? If I give you this example, all right, it says Hector keeps a record of the total number of clients he has and the amount he earns as a personal trainer. Tell if these rates of change are constant or variable. So we've got to go from 1 to 2. Remember that typically the input is what's in the first row or the first column, and the second is your y value. The second column is usually your y value. So change in y over change in x. Here we go. I went from $45 to $135. That goes in your numerator. Days, it was over 2 days. If I get this as a unit rate and simplify it, it's $45 per day. Okay, now let's go to the next interval, day 2 to day 3. You're going from $135 to $180. This is $45, and it's 1 day. Oh, that's the same as this one, this interval. Okay, things are looking pretty good. Let's keep going and test the last 2. From 3 to 4, 1 to 2, what am I doing? This was 1 to 3, sorry. This was 3 to 4. And then the last one, you can see when I typed this, I wasn't paying attention. The last one was from day 4 to day 7. That's this one. All right, from 180 to 315. What's the change in the money? Well, I went up about 135. That was over the course of 3 days. Simplify that, get it into its unit rate. That's, guess what? $45 a day. 45, 45, 45. These have the same rates of change for each of those intervals, and therefore, as it's climbing, and if you would graph it, these would be on an exact same straight line. There'd be no zigzags in it at all, and that is called a constant rate of change. That one's constant. Let's look at another one. And the number of tablets sold tell whether the rates of change are constant or variable. All right, so here we go. If I can get this computer to work, which it isn't. All right, now we're cooking. All right, from 1 to 3. X, Y. Change in Y over change in X. This is the number of tablets. So from here to here, 32 to 96, that looks like an increase of 64 tablets. And it's over a 2-week time frame. Put that in unit rate form. So divide 64 by 2. That gives you 32 tablets in 1 week. Next interval. I went from 96 to 128. That is 32 tablets. And from 3 to 4 is 1 week. 32 tablets in 1 week. What's going on here? Last interval. All right, 128 to 224. Let's see what's happening there. The difference is not quite 100 because I'm not getting to 228. I'm only getting 96. This is over a 4-week time frame. So let's get that one in simplest form. Now, lest you think that because this is 32 and this is 32, that this is just automatically going to happen. Afraid not. Because when you divide this, you're only going to get 24 tablets per 1 week. If you went and graphed this so you could actually see what it looks like, you're coming along from week 1 to week 3. Week 3 to week 4 is exactly the same. And then this one is only 24 instead of 32. It's going to be not as steep, more gradual or more flat. Not a constant rate of change. So we call this variable. It's changing. All right. Open your book. Here we go. So we've talked about this a little bit. Rate of change, and this, I believe, page 77. The rate of change is the change in the output over the change in the input. That's why I like to call it this way, because really I'm lazy and I don't want to write all those words. This notation is good for me. It's like painting a picture. Okay? You can read through that example on your own, but let's look at this particular one. Ooh, notice they're putting your table in a vertical format this way rather than horizontally. Same difference. Time is going to be your independent variable on the x-axis. Y is going to be the height. So here it says find the rates of change. So first we've got to go from 0 to 0.5. and 0 to 18 feet. Keep in mind the change in y over the change in x. I've got to say from 0 to 18, here's your first fraction. 18 over from 0 to half a second is half a second. Now listen, that's not the greatest number to put up there because it's not a unit rate. So take 18 and divide by a half. That is not 9. 18 divided by 2 is 9. This ends up being 36. So it's 36 feet per 1 second. All right, let's look at the next interval. From half a second to 1.5 seconds, it went from 18 to 31 feet. 18 to 31, that's 13 feet. Half to 1.5, that's 1 second. Not many feet. So this one, thankfully, is built in as a unit rate, so I don't have to do any simplifying there. 30. Right away, you can tell this is going to be variable. They're not the same. But I do want you to do this last one with me. Okay? From 1.5 seconds to 2 seconds, the height changed from 31 to 26. Careful. If it's going from 31 to 26, that means you're dropping 5 feet. Make sure you put -5 there. Half a second again. Okay? It's awkward to have those decimals inside the fraction. So simplify this to be over 1. -5 divided by a half is the same as -10. So if you graph this, what would happen is it would start pretty steep in that first interval. Then that second chunk of time wouldn't be as steep. And the final part actually is going to go downward because it's a negative value for your rate of change. Okay? Cool. All right. Take a look at the next page. I believe this is 78. Yes, page 78. You've done now calculating these intervals, looking at a table. What if you only have a graph? So here's how they're setting this up. They're saying, here's a graph. I'm picking specific data points that look like they're hitting on exact points in the grid line. So let's go from 1 hour to 2 hours. So that's from here to here, these 2 points. The change in the distance, that's the vertical part, went from 30 to 15, or from 15 to 30, I should say. But you really subtract the ending from the beginning. And you got 15, okay? That's over the change in time from 1 hour to 2 hours, which is just 1 hour right here. Notice when they're setting it up and showing you how they're figuring that, they're subtracting your ending point from your starting point, which is usually what you do. You get 15 over 1, or 15 miles in 1 hour. Next interval. Now, they're going to go from 1 to 4. So I'm going to change my color here. Now I'm going from 1 hour to 4 hours. So I start here, but then I'm grabbing this data point, 4,60. So from 115 to 460. My vertical change in distance, I went from 15 miles to 60 miles. So take 60 minus 15, 15, and that should give you 45. The change in time was from 1 hour to 4 hours. So take 4, or 1 to 4, yeah. 4 minus 1 is 3. Simplify this ratio, 15 miles per hour. All right, last one. They're asking you calculate the rate of change from 2 hours to 4 hours. So I'm using this point and this point this time, 230 and 460. So my distance, I started at 30, I went up to 60. So if you find the difference, that's 30. Going from the change in time, we were going from 2 hours to 4 hours. And when you subtract those, you get a rate of 30 miles in 2 hours, which as a unit rate is 15 miles per hour. Oh, these are all the same. Okay, this also happens to be a proportional graph. A proportional graph, of course, always has a constant rate of change. So it's asking you here in D, recall that when we graphed proportional relationships, they always went through the origin. So it's asking you, is this one with Nathan's time and distance, is this a proportional relationship? Yes, it has a constant rate of change and it goes through the origin. I'm going to abbreviate. You make yours look nicer, more grammatically correct. Okay? It contains the origin, which is 0, 0. Okay, so does a proportional relationship always have a constant rate of change? It does, because it's a straight line, which means no matter which interval you choose, it's going at that same slant or that same rate. Does it matter what intervals you use? If it's proportional, did it matter if we took the first two, the last two, somewhere in the middle? They all have the same slant or the same slope. So does it matter? No. All have the same rate of change. You'll get tired of saying rate of change pretty soon. We'll change gears and refer to it as slope eventually, all right? Okay, I want you to stop here, okay? We're going to save this part for next time. So what I would like you to do is come and check on Schoology for what your assignment is on these pages, and Good luck. May the force be with you.